Welcome back to the Explainer. If you hung out with us for part one, you know we nailed down the foundational concepts of pressure measurement. Well, today, we're skipping the agenda completely. We're diving straight into the actual sensing technologies used out in the field, and crucially, we're going to look at exactly where and why they fail.
Just to instantly ground us before we pop the hood and look at the hardware, let's do a super quick recap of the three pressure references from part one. Remember, pressure measurement always needs a reference point, right? First, we have absolute pressure, referenced against a perfect vacuum. Second, gauge pressure, referenced against local atmosphere pressure. That's what most of the instruments in your plant are actually reading. And third, differential pressure, which measures the difference between two distinct points. With that foundation set, let's look at how these instruments actually measure those physical forces.
Okay, let's dive right in. When you strip away all the fancy granding and the shiny metal housings, there are essentially just four principal sensing technologies used in modern process control to measure pressure.
What's really fascinating here is how clearly this illustrates the engineering compromises at play. We're looking at strain gauge, capacitive, resonant wire, and optical sensors. Every single one of these four comes with distinct trade-offs between accuracy, complexity, and robustness. There is absolutely no magic bullet here. When you select a transmitter, you're inherently trading away one attribute to gain another. And as you'll see in a minute, ignoring those trade-offs can lead to some major operational headaches.
Let's start with the absolute workhorse of the industry, the strain gauge. In a process control application, this is basically just a very thin wire or foil strip, usually some sort of chrome-nickel alloy, bonded to a flexible diaphragm. Now, as the process pressure deflects that diaphragm, the foil gets stretched. It's that physical stretch that increases the length of the wire, which in turn increases its electrical resistance. Wire those into a Wheatstone bridge circuit, and boom, we get a highly usable electrical signal. They are incredibly simple, exceptionally robust, and by far the most popular form of pressure measurement you'll see today.
Moving on to number two, we've got the capacitive sensor. So instead of stretching a wire, a capacitive pressure transmitter uses a diaphragm sandwiched right between two capacitor plates. The sensor gets energized with a high-frequency oscillator, and as the process pressure fluctuates, the diaphragm deflects. That changes the physical distance between the plates, which alters the relative capacitance. These sensors offer incredible accuracy, lightning-fast response times, and very low hystereses. Because they're so precise, this is the second most common solution you're going to encounter out in the field.
Now, our third technology is the resonant wire, and this takes a totally different physical approach. Think of it exactly like plucking a guitar string. You have a thin wire inside the sensor kept under constant tension. As pressure moves the diaphragm it's attached to, that tension changes, which alters its natural vibrating frequency. An electronic oscillator basically plucks the wire and senses that frequency shift. It gives you phenomenal accuracy and resolution, but, as you might imagine with a finely tuned string, it is extremely sensitive to its surrounding environment.
Finally, we have the optical sensor. This setup uses an opaque vane mounted directly onto a diaphragm, moving right in front of an infrared LED light beam. As pressure shifts the diaphragm, that vane physically disturbs the light hitting a measuring diode. Because optical sensors need barely any movement to get an accurate reading, and because there are literally no physical linkages to wear out over time, they offer incredible precision with negligible hysteresis. The catch? The complexity of those optical components makes them a pretty expensive option.
So here's the crucial point. We have some incredibly precise instruments at our disposal, but here is the hidden trap. That lab-grade, high-accuracy you're buying with a capacitive or resonant wire sensor often comes at a massive cost, and that is a severe sensitivity to environmental vibration. What works flawlessly on a pristine, quiet test bench can instantly become a liability when you bolt it to vibrating heavy machinery.
Let's actually test this with a little interactive challenge based on real-world plant realities. Imagine a massive reciprocating compressor skid. It's heavy, it's loud, and it is vibrating intensely. Now, you need to measure the discharge pressure with high precision. Knowing what we just talked about, would you take a high-accuracy capacitive transmitter and bolt it directly to that vibrating discharge line with zero isolation? Take a second and think about the physics we just went over.
The answer is a huge, resounding no. A vibrating compressor skid will slowly but surely destroy the accuracy of that transmitter. All that vibration mechanically agitates those delicate capacitor plates, or the resonant wire if you used one of those. What happens is the controller receiving the signal ends up frantically chasing noise instead of actual process changes. Without isolation, your accuracy is totally degraded, and honestly, nobody usually notices until the safety system is right on the edge of tripping from a false reading.
Let's turn these insights into some practical rules of thumb for surviving heavy industrial realities. To prevent those false trips and erratic control loops, you've got a few solid options. First, just avoid placing resonant or capacitive sensors directly on rotating equipment unless you have heavy isolation. Second, you can always downgrade your lab-level precision and just go with a more vibration-tolerant technology like our robust friend, the strain gauge. Or, third, if you absolutely have to use the sensitive tech, install a remote diaphragm seal and connect it to the transmitter using flexible impulse tubing. That'll physically dampen the vibrations before they ever reach the sensor.
All right, now that you know how to avoid the vibration trap, let's pivot to what I like to call the ultimate industrial multi-tool. There is one single technology that pretty much rules the plant, and that is differential pressure.
Differential pressure, or DP transmitters, are hands down the most versatile instruments in any facility. This single physical technology, which just measures the difference between two pressure points, handles three completely different jobs. First, it measures flow rate by looking at the pressure drop across an orifice plate. Second, it measures the liquid level in a tank by calculating the hydrostatic head pressure against a known density. And third, it detects filter fouling by measuring the pressure drop across a filter element. It's literally one piece of hardware cleverly adapted for three vital plant functions.
That differential pressure backbone is so crucial that it actually forms the basis of the most common flow measurement technologies in the entire industry. But what happens when you're dealing with fluids that just don't play nice? Fluids that are incredibly viscous or highly corrosive, where restricting the flow just to measure a pressure drop isn't even an option. Well, that requires a completely different philosophy. In our next explainer, we're going to explore flow meters, comparing energy extractive methods against energy additive methods like magnetic and ultrasonic flow meters. Until then, ask yourself this: how much energy is your process giving up just to measure its own speed?